Okay, so I think on the program it says the difference between walking and running, but here's the topic. If you walk or you run, you use some energy and you have some preferred step length. And when you pick this preferred step length, that determines energy use. And you can look at what happens if you vary gravity and what happens if you vary speed. And what we found out, and we means Ryan, who's here in the back row, more or less, what we found out is that the energy cost is sensitive to speed, but not gravity, for walking. But for running, it's sensitive to gravity, but not speed. And that's an approximate description of the data. So I'm going to show you the data, and then I'm going to show you a theory, very crude theory that predicts the result. So let me start by describing the experiment. So the experiment is kind of standard for these anti-gravity experiments, which is we can't anti-gravity on the whole body, but we think the most important part is gravity on the upper body. So you just pull up. And you pull up, and you don't want to pull people forwards and backwards, so you pull on a trolley. This trolley is free to slide, so these are capable to stay vertical. And you pull with a constant force, and if the force is half the weight of the person, you call that G over 2, half gravity. And you could have a quarter gravity or 3/4 gravity like this. So then the question is, how do you apply that force? And you're now going to have just a digression on the experimental equipment. So for those, this is just sort of a mechanics digression for those who are curious about that. So how do you get a constant force? Just one of the standard ways is to make a very soft spring. How do you make a very soft spring? You make a very long spring. Well, you can't buy very long metal springs, so people do very long rubber springs. You take rubber tubing, surgical tubing, and 50 meters of it or so, wrap it around pulleys, and then pull on this. Or you can put a DC motor, like Heike Valerie has done for her suspension, which is for a different purpose. Or you can hang a weight, and then and make the weight be the amount of anti-gravity. Now, one of the problems with these is this has a lot of hysteresis. As you're going on this machine, you're going up and down, and if there's friction in this system between this point here and wherever you're pulling, then there'll be a friction force one way and friction force the other way, and those two friction forces will add up to give you different effective tension here, depending on whether you're going up or down. That's a bad simulation of reduced gravity. DC motor is expensive. We did this basically with no budget. And you can hang a weight, and if you hang a weight, though, then it adds inertia to the system, which is not a parameter we want. If you want to take inertia out, you hang a heavier weight and put it on a lever. So if you take a weight that's 10 times as big as the person, let's say we want to make zero gravity, 10 times as big as the person, and reduce it with a lever by a factor of 10, then the effective inertia also goes down by a factor of 10. So make the inertia low, ironically, you make the mass more heavy. Anyway, we didn't want to do any of these because we didn't like the hysteresis, we don't have the money for the DC motor, and we didn't want to have a 10-ton weight in burlap. Okay, so here's the system we made. This is a little complicated, so I'm just going to break it down and show you how this works. So it's a little bit clever, I think. It's based on two patents from 1938. One of them was for a long period seismometer, and the other one was for a light that's self-balancing in different positions. So the idea is we have a lever here, and we're going to pull, and this is going to be the pulling force. The reaction to this one is going to be the pulling force on the apparatus. And we want this force to be constant. If you have a spring here, and this is fixed, we get tension in the spring, that pulls us this way, and that's what's pulling on the apparatus. These two are fixed up here. Now what we use is what's called a zero rest length spring, and a zero rest length spring is a spring where the tension is a constant times the length minus the rest length, which is 0, so the tension is a constant times the length. It's a spring that, when point C is all the way back here, has 0 tension. And such springs do exist. There's several designs for them, but they're kind of oddities, so we didn't want to have to deal with that. But let me just explain how that, if we had such a spring, how it would work. Well, the tension here is proportional to this length, and it's in this direction. Therefore, the force on this thing is proportional to the position of this relative to this times the spring constant. That's the force vector. The force vector is k times the relative position. But this position vector here, we can get by adding a position vector here to a position vector here. That's some of these two. But let's look at this one here. That's the force along this rod, and it has no moment about this rod. So only this one it contributes to the tension here, and that's a constant. So this apparatus is equivalent to putting a constant force over here. And if you look at the geometry of this, this is a constant force independent of angle. Okay, so the force effective is just the one from here to here. Then that gives us this constant tension, which all of these are constants independent of this angle theta. Okay, so here, this is the way the apparatus works in whole. This contraption replaces a zero rest line spring with a regular spring that is attached to a line, and the line is set up such that when point C is back here, the spring is relaxed. So we build an effectively zero rest line spring by using pulleys and a regular garage door opening spring.
Has this been patented?
Say again?
Has this been patented?
Well, the only innovation here compared to those 1938 patents is making a zero rest line spring with a pulley. And knowing about the patents, right? It's the clever things to know about the patents. Okay, so how does this work? Okay, so it works pretty well. So, we did experiments, meaning I never saw the experiments or had anything to do with them. With a bunch of people who were men and women and maybe some non-binary people, I don't know, and different masses and so on. And here's the results. I'm going to show you 4 different graphs. So here's the energy use, which is the cost of transport measured in relative to mass, not weight. And what you see is running at high gravity, the cost of transport is independent of speed, but it depends on gravity. Whereas if you look at walking, we have high gravity, low gravity. High gravity, low gravity, there's a big dependence on speed, mostly independent of gravity. So the caricature of this is some line that goes up, and these are 2 level lines. If we look at energy use versus gravity, the walking does depend somewhat on gravity, but just not very much. So the caricature of that is this is a flat line, and running, the cost of transport does depend on gravity. Now, both of these are consequences of the person's choice of step length, and so you can look at that choice of step length versus the various parameters. So here's versus speed, and these are both slope climbs, but this is sloped more. So we're just going to stereotype this as this is a level line, this is a slope line. That's a little bit of an exaggeration, but that's that's the trend. And here's a different way of plotting it, which is instead of plot gravity, look at the different speeds, and you see that the step length as a function of gravity is almost not at all, and as a function of speed, it's not very much. Right? These are all compressed. And then we don't have running at 2 different gravities. But you see there is dependence upon the running step length on speed. Okay, that's the caricature of the experiments. And here they are all together. The main thing to remember, the main one is that it's just the cost of transport for running, cost of transport for walking, and how they depend on speed and gravity. Okay, so now what about getting a model for this? Here is everyone's favorite model. It's a point mass with legs that are massless for some purposes and not for other purposes. Or you could say the mass of the legs is incorporated in this for some purposes and thought of as separate for other purposes. And then here we have our model of walking and our model of running. The model of walking is that the mass goes on a circular arc, and then there's this what Art Gould calls a step-to-step transition. One foot goes down, and the swing foot becomes a stance foot. Then in running, it's just a single leg at the step-to-step transition, but there's a collision here. Now, assumptions that we're going to make is that how fast is the swing here? Well, it's fast enough so that when you swing back, you match speeds with the ground. So we know the speed of the swing foot
10 minutes.
used up.
Yeah.
Okay, so we're going to assume constant horizontal velocity, which is sort of ignores this increase and decrease in energy during the stance phase. Okay, so the big assumption is that energy cost can be broken up into a sum of two terms: a cost for swinging the legs and a cost for support, or collision, or step-to-step transition. And now just to answer the question, what's the difference between walking and running? The key difference, at least in this calculation, and I think this really is the key difference, is that in the flight phase of running, you're on a parabolic or arc. And in the flight phase of walking, well, it's really not the flight phase, it's the stance phase, but it's sort of serving the same purpose. It's a bridge between two collisions, or a bridge between two step-to-step transitions. It's a circle. Now, what's the difference between a circle and a parabola? Not much if you match them, but a parabola could be way up here and way down, or it could be way flat. So what happens is, for a given step length, depending on what speed you pick, the parabola changes its shape, and the circle does not. Okay, so what comes out of this is we can do a collision calculation and look at how much energy is lost when you bang into the ground, and figure out what that is in terms of the speed and the step length. You can look at how much energy it takes to build up the speed of the swinging leg, ignoring the gravitational aid that you get in walking but not running, and you get a term that has this v squared, omega squared, and a bunch of constants. You can add those up and you get this formula here, which looks like this if you take all these constants, masses and minus as constants. It's a v squared times something times d plus something divided by d. And then you take this and we want to minimize it to the cost of transport, because that's surely what people do, maybe. And you get a formula for step length, and then you can plug that back into this cost of transport, and you get this is the predicted cost of transport as a function of speed. And what do you see? It goes a speed squared.
Well,
so you go faster when you're walking, you have a faster collision, and then the energy goes with the square of that. And the step length, interestingly, has nothing to do with gravity or speed for step length. So you do the same calculation for running, working out the collision, and the arrows just point at the key variables. The total cost of transport now is a different form than last time. This collisional term is this collisional term is different, and that's the big difference right there. So what you get, this collisional term is different. And the key thing here is that when you go faster, the collision loss is smaller in running. You go faster, and the parabola is more shallow. The vertical distance you fall between steps is less, and it's less energy loss per collision than a faster run at a given step length, whereas for walking it's more. So when you differentiate to minimize it, you get a different step length as a function of speed and gravity, and then you take the total metabolic cost, and it looks like this. And it has gravity in it, whereas walking did not. But it doesn't have speed in it. So that's the result. It gives these curves. And here's just a comparison of the experiment and this theory, is that we can say, here's this curve, two flat lines for running, and this curve going up for walking, and that's like the big victory of this theory. The rest of the graphs are a little more questionable, especially this one, which predicts that the step length is independent of speed, whereas the step length actually does depend somewhat on speed. But at least it gives a smaller dependence for walking than it does for running, just like that one does.
14.
And that's the deal. So what's the difference between walking and running? Is that in running you have a parabolic flight phase, which gives a smaller vertical collision for a given step length. And for walking with this flight, which is like stance, you get a bigger collision if you go faster. Therefore, when you optimize the step length, you get a different step length, and then when you put that back into the cost of transport, you get different dependence for walking and running. And that's the whole story.
Can you comment reduced gravity. Ryan and I both talked about how easy it is relatively to learn this task compared to max doll and exoskeleton type things.
Why don't you comment on that?
Did you find it easy to learn also? Like, or did you try to?
Let's see, I was a victim of this experiment for about 5 minutes and I found it painful.
Oh.
I didn't find it easy at all. I just started putting on being supported by your crotch.
Your calculations somewhat depend on the assumption that you have glancing contacts.
And we have what?
That you have glancing contacts and running the vertical leg.
That's right.
And when we actually run, we land with an angled leg.
That's right.
And we take large amounts of steps, and that angle becomes more shallow.
It does become more shallow. That's what we predict for running. That's all that. So this does have just an instantaneous contact. It doesn't have that there's a landing angle and a spring-like motion here. But it does say that when you run faster, this parabola shrinks, this angle goes down, and that's why the cost of transport goes down for running when you run faster. But it doesn't go down if you adjust the step length appropriately.
I think I want to go in the direction that you are making shallow and shallow angles when you contact, and that should increase your effect when you run faster.
Well, it decreases your collision, your vertical collision velocity.
But your horizontal.
No, we have no horizontal collision. We only have a vertical collision.
You do, but humans.
What?
Humans have a horizontal collision.
Somewhat of one. So that's not in this model. So the model is highly defective. No one said.
At least used to have the collision mostly aligned with the center of mass, so it's almost vertical.
Yes, there's lots of things missing from this model. So a game we could play is say, oh, we're going to improve the model this way, and we're going to put a more realistic swing cost in, and a more realistic collision cost, and we'll take into account the tendon, and do an accurate calculation of the energy savings from the tendon, and the energy savings from using a complicated mechanism that absorbs all the energy. We could put in 3 lengths and 3 dimensions and so on. And eventually we'd have a very good model. What would we find? We'd find this. Otherwise it's not a very good model. So we know that we can go, if there exists a good model, we can get closer and closer to this by including more and more realistic features. So if I'm going to advertise this, it's not that it's a great model of running and walking. It's a model that has the minimal features to predict this trend that running is almost constant velocity, constant energy with speed, walking increases, and then the step length, the trend, this other trend. Sorry, that's just it. Walking, this thing. Black line and red line are different, these 2 plots. Right, does that answer your question? I mean, it's any simple model you can complain about it, right? Is this a great model? Is it like, oh, it really it condenses everything into one simple unified theory, like Art's model did? It doesn't do that. Yes.
So I'm super curious if there are features of human morphology, stiffness in like tendon gradient, et cetera, that are tuned for 1G. Like that would be really interesting to see if we could get at that with these kind of experiments and models.
I mean, if I was going to address that question, I would ask the simulators how it works, how well they do it, how well their runners and walkers could work if they change the stiffness of the Achilles tendon. Yes?
From my experience, like I rode like Hector Mallory's device, and I found it very difficult to keep ground contact with reduced gravity. And so I think your velocity band goes down to like 1 meter per second. And I wonder if there might be compensation mechanisms, and only at lower speeds you might see a speed dependency because people have to my question I think is the energy consumption that you measured in your subjects. How is that measured? Was that also the mechanics that you presented, or was that like?
No, so, indirect calorimetry,
Yeah.
VO2.
So I'm wondering if there is some
At
compensation.
low speed, okay, so at low speed, the model goes especially bad because we assume that the speed is constant in walking, and it's very much not constant at low speed. And we assume there's no gravitational contribution to swing, and that gets to be very important at low
Yeah.
speed. And the graph, if we look at the data for some things, like this one, there gets to be this curve, which I'm trying to say is flat. It's less and less flat down
Yeah.
here at low speed in the experimental results.
That's.
So I'd say that the theory is bad here. Now, as far as the data, it's weird to walk in low gravity, we only went down to G over 2 to half because it's weird. It's too weird, less than that. I think it's a too high a pain to lift
Yeah.
ratio.
How does that graph look like when you normalize for gravity? Like when you use fruit numbers and cost of transport?
Yeah, I
There are
didn't
two
do
graphs
that.
back.
I didn't do that because it's too confusing. You know, the right way to normalize cost of transport is by weight, not by mass, because you get a dimensionless measure.
But then the running lines are on top of each other, right?
The running lines are approximately on top of each other, yeah.
And when you
Approximately.
normalize by speed,
So what?
when you normalize by speed,
What do you mean by normalized?
or by a use fraud number.
So Freud number would just be an adjustment for subject to subject variation. The question is, do we reduce the subject to subject variation by normalizing by speed? And the answer is no.
But G's in there.
And G's in there too, yeah. So, you want to, I have to think about it. How much you get by doing things in a non-dimensional way. I haven't thought it through.
Philip?
So as far as I know, when you're in low gravity, hopping is more efficient than walking, as far as I know. But if I would model hopping the way you would do it, it's very similar to the running gait.
Well, if you look at let's say just look at this curves here, and you say when's the walk to run transition, it's at this speed for high gravity, and it's down here at a lower speed for low gravity. So this does predict that the walk to run transition, the speed goes down when gravity goes down.
Oh, sorry, hopping.
Well,
Skipping.
hopping is, at this level of detail, hopping and running are the same thing.
I think it means skipping, and then it's, in this model, it would be.
Well, then 2x skipping is a sort of a hybrid. And I don't know if that, that seems to be true, the astronauts do it. I don't know if that's true in good simulations, so I don't know if people trust their simulations enough to agree with that in terms of whether the energy theory predicts that.
How much do you think arm swing will be affecting your cost of transport? Because that isn't affected by the gross gravity simulator.
Well, I mean, arm swing does affect the cost of transport, and swinging your arms does reduce the cost of transport. That's a fact, it's not very much. Then how does that change when gravity gets small? I don't know.
Was there?
Yeah, my question relates basically to the question from Hartmut. You said that you have a good model which can predict what you found in.
No, I'm saying if you say, oh, this is not a very good predictor.
No, that's
I don't
fair.
have a
But
good model.
I just want to see if we can then conclude that based on this model, the cost is mainly related to the impact. So is it the main reason for cost? I mean,
If I wanted to improve this model, the first thing I would do would change the swing cost to prove that the cost of swing is not exactly work. It has some rate terms that our cool likes, wherever it is. There it is.
Eric?
Where is our cool?
Yeah.
What? Okay.
Getting back to the cost of transport doesn't have gravity in it. If you put gravity into your cost of transport, wouldn't that mean that the running doesn't depend on gravity and the walking now does?
Yes.
So that's the opposite of what the conclusion you originally said.
Yes.
That doesn't bother you?
It's just that that normalization by gravity is I don't know, it's just a weird thing that I like it down here on Earth, but when we're comparing different planets, it just confuses me.
You like it when it's a constant,
Yeah, I like it when it's a constant.
when it's an arbitrary constant.
Yeah, but it's a good point. The result is exactly reversed. if we use the normal cost of transport, which frankly, I don't think any of us have a good intuition for when we're varying gravity. Speaking for myself and extrapolating to others.
Thank you, Amy.
The last question from Little Roach.
Tagging on Philip's comment, you also see skipping emerge when people are going down really steep inclines, or like lemurs will also skip. So can you apply this kind of analysis and instead of looking at gravity directly, look at the ratio between inertia and weight or something like that?
I don't know. But I do know what at dynamic walking some years ago, we had a little group of people started talking about, do people skip? Like, is that a gait? Two people started with 2 people, and then we both kind of admitted that sometimes we skip, and then a third person came and said, do you ever skip? And they go, well, when I'm all by myself. Turns out everybody skips sometimes. I mean, you could do a little.
So on flat ground,
it's a very private activity.
On flat ground, skipping feels great, but it's really exhausting.
What?
On flat ground, skipping is really exhausting.
I don't know if that's true.
I can say it's true.
I mean, like, the conjecture is that, like, for some weights and scales, it's not so costly, like for kids.
Yeah.
But I don't know. Does anybody? I don't know the answer. People I know by experiments or by calculation.
There is an experiment that did this, but I don't know the number.
But I think it's exhausting actually because you have to tense your core muscles a lot just to, like, the frequency is just really bad for your wobbly muscles and stuff.